Good afternoon. It is my honor and privilege to introduce the Honorable Vice Chancellor, Professor Bhairappa, who is giving this talk. There is a very long list of his achievements, but then you have been, as a Vice Chancellor, he is very well known, and moreover, since yesterday, you have already heard many things about his achievements, academic qualifications, and so on and so forth. Since it's my duty, let us read, I will read a part of whatever he has achieved. Professor Bhairappa is a renowned academician and researcher for over a very long time, and he has published 335 research publications in international journals, which has a very high citations, 5,900 citations, and he is a world authority on hydrothermal technology. In fact, he has a book which is called Handbook of Hydrothermal Energy, which is published by Elsevier publishers, and it has seen 2 editions, and the 3rd edition is in preparation. This is a very excellent academic recognition of his research and so on. He is serving as an editor-in-chief and senior associate editor, and also editor of several international journals from highly reputed international journals. Just a few of them. 5 special editions of material science journals published by international publishers from USA, UK, Germany. And apart from that, he is an elected fellow of the Royal Society of Chemistry, London, UK, elected fellow of World Academy of Ceramics, Italy, and also an elected fellow of Asia Pacific Academy of Materials, Japan. Also the Secretary General of Asia Pacific Academy of Materials. He has received several awards like Dr. Raja Raman Award for Science and Technology, highest award from Karnataka government, Sir C.V. Raman Award in Physical Sciences, Material Research Science India Gold Medal, and Golden Jubilee Awards twice during 87-92 for best research work in the University of Mysore. Very recently, he was awarded the Sir C.V. Raman Birth Centenary Award for the year 2016-17 by the Honorable Prime Minister of India in recognition of his contribution to science and technology in India. This is a honor not only for Mangalore University, but Karnataka itself. Also, he has received the Attractive Paper Award in 9th International Conference on Crystal Growth held in Japan during August 1989. Also conferred the Educational Leadership Award by Vijayawani, Bangalore, and also serving as the international bodies of Indian National Science Academy. Currently, he is serving as the Vice Chancellor of Bangalore University, which you all know. And then he is involved in several innovative programs in the university to promote science as well as academic activities and so on and so forth. Which I have heard how in the last 3.5 years he has involved in bringing many conferences and so on. Apparently, I heard the convener telling that over the last 30 years, in the last 27 years, the number of conferences were much less than whatever the conferences he could have in the last 3.5 years and so on, bringing international reputed academicians and like that. And apart from all these things, I would like to say a few personal things which I was lucky enough to have it. About a decade ago, I went to the Mysore University Geology Department and I had an occasion to visit his lab. And that was a fantastic experience because using high pressure and so on, they were actually synthesizing artificial diamonds, which is for industrial thing. And at university level, producing this was remarkable. The other thing about it is about a year ago or so, I had the privilege of attending one DST inspired program in a place called Pilikula, maybe about 20 kilometers from here and so on. And this was for the workshop for the 11th standard students, you know. So you have to give lectures to them and so on and so forth. Here again, Professor Bhairappa gave a lecture, and the speciality is he is an authority, he is writing papers, books and so on. But, you know, he came to the level of the 11th standard students and conveyed the subject in such a lucid way, which was fantastic. Only an expert who has a depth, you know, complete understanding can give such a thing. That is the Honorable Vice Chancellor, Professor Bhairappa. And Professor Bhairappa is now going to give a talk to us on fabrication of advanced functional nanomaterials of metal oxides and their composites. Professor Bhairappa.
Thank you. Thank you very much, Professor Suresh, for the nice and very lengthy introduction. First of all, I would like to thank the organizers from the Department of Studies in Physics, Bangalore University, for giving me this opportunity to share my research experience and what we have been doing at the University of Mysore for the last 3 decades or so, and also to present some new research findings from my group. The topic of my talk is the in situ fabrication of functional metal oxide, nanostructures, and their nanocomposites. I am going to speak on the following aspects: introduction, how we prepare these nanostructures of metal oxides and nanocomposites of these metal oxides. And I will also speak briefly about the in situ fabrication, what does it mean, and what processing methods we adopt, and in situ surface modification. And then I will speak on the synthesis of metal oxides and the composites and the functionalization of these metal oxides and the composites, and summary at the end. Well, very popularly known processing methods or the fabrication methods are listed here, and I have published in Journal of Ceramic Society of Japan. And I am specialized in these two hydrothermal, solvothermal methods and supercritical fluid precipitation processes. And these two are very popular. However, if you look at the figures, not so high, but to get high quality products, these two are very good. And also, particularly the supercritical fluid precipitation process is extensively employed in the crystallization of various pharmaceutical products or drugs crystallization. Well, as I said, I am going to cover mainly the two topics, two techniques, hydrothermal and supercritical processing techniques. Let me give a very brief tutorial for those who are not very familiar with the hydrothermal processing or the hydrothermal technique as such. It can be defined as any homogeneous or heterogeneous chemical reaction in the presence of an aqueous or non-aqueous solvent above the room temperature and at pressure greater than 1 atmosphere in a closed system. And this is nothing but a solution processing which began during 1850s by the geologists to understand the formation of various ores, rocks and minerals deep within the earth crust, but today it is a very popular subject, particularly in nanotechnology and in hydrometallurgy. And this was referred earlier only to the high temperature and high pressure processes and environment highly loaded. And I am going to show how we have changed it from highly environmentally loaded to the environmentally benign, which I am going to talk in the future slides. In recent years, it is being treated as environmentally benign, and in fact, it's a part of the green chemistry, and even, as I said, suitable in the crystallization of several drugs. Because we use carbon dioxide as a solvent in the drug manufacturing, and this carbon dioxide has a critical temperature around 37 degrees C, and you can crystallize any of these drug or pharmaceutical products at around 40 degrees C. That is the advantage of this supercritical hydrothermal technique. Well, the most important thing in any hydrothermal reaction or processes is the presence of solvents and some organics. Well, this is a recent addition, the presence of organics, but the hydrothermal normally refers to the presence of solvents. Well, it can be both aqueous solvents or non-aqueous solvents. I have listed the commonly used aqueous solvents. They may be even acidic or alkaline. And under non-aqueous, we commonly use glycol-based or butyl alcohol-based and methanol and so on as the solvents in carrying out hydrothermal reactions. Well, these are the commonly used aqueous solvents. Well, I said about the organic additives. The presence of organics under hydrothermal conditions, as per the earlier definitions, was not believed, even though some earlier experiments were carried out during mid-30s by the German chemists. But after the discovery of rich organic life deep in the sea, the marine hydrothermal vents, people started believing the role of organics even under high temperature and high pressure. And that is how, particularly in 80s and 90s, people started using the organics in hydrothermal systems. And there are different roles played by these organics, maybe as solvents or even as additives. But these organics play an important role, particularly in the processing of nanomaterials, in controlling the particle size and the agglomeration of the nanomaterials, and in many cases even to enhance the reaction kinetics. In fact, the reactions which I used to carry out in 7 days or 10 days, now I have brought down that temperature, the time duration to several minutes. And in under supercritical conditions, in one particular case, I have obtained very high melting compounds of rare earth vanadics, which have normally melting temperature above 1800 degrees C. Such materials I have obtained at temperatures under supercritical conditions within a fraction of seconds, or even about 5 seconds, with highly controlled size, morphology, and tuned or the tailor-made properties. Well, these are the this wave graph shows the current trends in materials processing under hydrothermal conditions. In the earlier days, as I mentioned, hydrothermal was referred to very high temperature and high pressure processes, and I have listed some of the compounds which we have worked extensively, and these are the experimental conditions used by the earlier workers, and this third column shows the experimental conditions we have used, and you can see a very significant drop in temperature, and accordingly the pressure less than, in this case about less than 30 bars, and here less than 100 bars. That's a great contribution to the field of hydrothermal technology. This we could do based on the understanding of the thermodynamics and the solution, hydrothermal solution chemistry. And this is how we could synthesize diamond and under subnatural conditions. This is a very significant work, and this is the most highly cited papers with over 800 citations. Well, under hydrothermal technology, now in recent years, instead of carrying out experiments through empirical basis, and instead of carrying out thousands or hundreds of experiments, which people used to do in the earlier days, and at the end of the experiment, after a very long period, if you take the example of quartz or ruby crystal growth practiced during 1880s and 1890s, Even after 3 months after carrying out the experiment in the hydrothermal autoclave, when once the autoclaves were opened, they found nothing, the crystals didn't grow. So in order to avoid all such experimental losses, people are using the thermodynamic modeling or the computation methods to understand these stability field diagrams. And we have done this type of calculations for the hydroxyapatite system and also for the PCT system. And the advantage of this is, instead of carrying out hundreds of experiments to identify the precise PT region for the growth, or PTX region for the growth of a particular, or the crystallization of a particular compound, you can here calculate calculate using the thermodynamic parameters and construct the phase diagram, and also find out the stability field and calculate the yield of the product. And you can very easily identify the single phase formation region and also the maximum yield. Well, if you take very expensive rare earth compounds in your experiments, and if you do not get in your product all that raw material what you have taken, then it's going to be a big loss and very expensive. In order to avoid that, the yield diagrams would help you. Whatever the raw materials you take, all that would be converted as the product what you desire to crystallize. So about 99.999% of the raw materials can be converted to the final product designed by you. And this is the advantage of these stability field diagrams. We also call this thermochemical computation and the yield diagrams. Well, this is the strategy we adopt to fabricate in situ the metal oxide, and also we modify the surface properties of these metal oxides. The principle adopted here is from a kitchen experience by adding a few drops of oil in the boiling of noodles. Will not make the noodles very sticky. The same way we use some fatty organic acids which are popularly called surfactants, and these surfactants do not allow the nanoparticles to agglomerate, and also do not allow the nanoparticles to grow in particular directions, or also also it will hinder the growth of bulk or the bigger particles of the metal oxides. Well, under normal conditions before the hydrothermal or solvothermal treatment, the fatty organic acids like oleic acid or gluconic acid and so on, the organic will remain at the top, as you can see here, top layer, and your solvent may be organic or inorganic. Normally, this represents the aqueous solvent, and the metal oxide source existing separately, and as you can see the species. And during the hydrothermal or solvothermal treatment, you have the homogenization of the raw materials, and the hydrolysis or dehydration reactions occur, and you have the formation of such metal oxides or hydroxide species which have the organic coating around. And after the experiment, when you cool the reactor, you have the metal oxides and surfactants coming up, as you could see here the surfactant at the top, but the metal oxides also move to the organic side, and you have the aqueous solvent which you can easily removed. And this is the popular strategy being adopted in recent years in the processing of metal oxides and other nano materials under hydrothermal conditions to give the desired properties or tailor-made properties, whether it is biological properties or the physical properties under hydrothermal conditions during the growth. That is why it's called in situ fabrication. Well, this wave graph shows some characteristic photographs, temp photographs of the metal oxides. These metal oxide images, temp images, represent the absence of surfactant, and here these metal oxides have been obtained in the presence of surfactant. Of course, I have not listed the type of surfactant used, and these are the metal oxides shown here, and they are so beautifully arranged. Self-assembly of these metal oxides you can achieve under hydrothermal conditions. And you may ask how much, how thick these organics coating over the metal oxides, and this is the high resolution TEM image of Syria nanoparticle of about 7 nanometer size, obtained with deconoic acid as a surface modifier, and the nanocubes are arranged so well, and you have a very thin layer here of organic, which you can remove through sintering at around 500 degrees C, and the organics can be eliminated, but still you can retain the same size and shape for these nanoparticles, and also unagglomerated. And this is how we can control the morphology of various compounds. PZT, for example, you can obtain as needles, long needles, or acicular, habits, what we call. Or you can also obtain the same PZT crystals as beautiful cubes. And similarly, the titanates, the potassium titanates, you can obtain either as hexagonal plates or as wires, very long nanowires. And in fact, you can, this is what is required particularly in metal oxides and other compounds for the nano-cosmetic applications. The plate-like morphology is very useful. Well, this is an imagination. Well, it used to be some years ago, an imagination of the author. To have, if you can understand the thermodynamics and the solution chemistry, hydrothermal solution chemistry precisely, it becomes very easy for you to prepare a wide range of compounds. In fact, throughout my days in hydrothermal research, all through my hydrothermal research days, I have worked on various compounds, and in fact, some Japanese scientists have listed this, compounds through this kind of periodic table of elements, and giving that most of these compounds were prepared by my group. So that made me very happy, and then I could come out with this imaginary, what you call nano vending machine. But now people have already started working on this on trial and error basis by some companies in US, California-based companies. They are working on obtaining the nanoparticles of desired size, shape, and properties by by selecting the appropriate temperature, pressure, and what size you require, and the surfactant, the solvents, and various elements, the combination. And the machine will automatically calculate the kinetics and the thermodynamics based on your selection, and if everything goes well, and instantly you can get the nanoparticles in seconds. So that is how this was visualized, and now it is already in practice on experimental basis. As I said, in situ fabrication, that is the main focus of my talk. This deals with the surface modification under hydrothermal conditions in order to obtain desired size, shape, structure, surface chemistry to the products, and also to achieve a desired crystallinity, phase purity, physical, chemical, and biological properties. You can tune these physical, chemical, and biological properties to the products through this in situ fabrication, through surface modification in particular. And of course, these are further controlled by the experimental conditions. In addition to the surface modification, you also require a desired temperature, pressure, pH of the medium, solvent, the type of solvent, the type of surfactants, and the concentrations. All these, if you can control precisely, you can get the tailor-made properties with, tailor-made products with desired properties. And these are the products I am going to cover in my lecture: zinc oxide, titania, and also a composite cesium oxide, bismuth oxide, and zinc oxide, and bismuth vanadate, and the graphene, and the composites. In fact, yesterday we heard nice talk by Professor Chennupati Jagadish, and he did mention about the zinc oxide and titania very briefly. And in fact, pure zinc oxide and titania are not very popular these days due to so many reasons, and people are going for such new compounds very recently. And I'm going to show here some unpublished data in my talk. This shows the schematic diagram, the flow chart of the experimental procedure adopted in the fabrication of these metal oxides and the composites under hydrothermal conditions. The raw materials or the precursors along with the dopants, if any, are taken with the required mineralizers, maybe aqueous or non-aqueous, and the desired surfactant is taken. And this slide shows the experimental parameters like temperature and pressure, and the duration of your experiment. It can vary from 2 hours to 48 hours. And in fact, we have further reduced to about 30 minutes in some of our experiments with the addition of some organics. So hydrothermal is becoming very handy and very economic due to all these developments. And the raw materials under these temperature and pressure conditions, when they are treated under hydrothermal conditions, you get tailor-made metal oxide nanoparticles or the nanocomposites, which we have used in various studies or applications related to the biological applications and also photocatalytic applications. These are some of the sun images along with the schematic diagrams of these metal oxides, pure and doped. Here you can see the pure zinc oxide surface modified, showing this typical morphology and the facets which are indexed. And when indium is doped for the zinc oxide, you get a different morphology. And when you have tungsten, you get hexagonal platelets. And when you have the molybdenum doped, you get a scalenohedral morphology. And we have also doped a couple doping like with the ruthenium and this silver. You get this kind of beautiful morphology with reduced aspect ratio even and hexagonal platelets. And you have here the ruthenium and the palladium doped, and the morphology can be tuned this way, and even the size can be controlled this way. Well, I have listed here some of the surfactants we have used and the morphology obtained accordingly. When gluconic acid was used, we obtained flower-like or nanorods, and when oleic acid was used, we obtained some hierarchical structures. Tween 80, when it was used, we got the nanogranules. Gallic acid gave nanorods. Thymus vulgaris gave nanoplates. And even honey was used, we got some nanospheres of these zinc oxide. And diethylenamine was used, we got some nano needles or nanorods. The effect of surfactant on the zinc oxide morphology is shown here in this wave block with different surfactants like gluconic acid and CTAB and DEA, and this is CTAB and diethylenamine, and they show different morphologies depending upon the concentration and the type of this surfactant. And here you can see the gluconic acid giving these flower-like nanorods and some hierarchical structures, and oleic acid giving this suppression of 001 growth, and tween 80 giving this typical morphology for zinc oxide. And thyme leaf extract has been used as the surfactant biomolecule in controlling the properties or tuning the properties, size, shape, and the biological properties, and we get this kind of morphology, and the growth direction is completely changed. Now, we have also discussed the heterogeneous growth mechanism of zinc oxide nanostructures with the additives or the surfactant concentration with time, and this was published last year in the Royal Chemical Society Journal, and this is how the morphology varying with the decreasing in the additive concentration, all these. And we have proposed two different models for the understanding of the formation of these different morphologies. The model 1 comes with the 5 different stages. Of course, these are based on the concentration of the growth units. The concentration of the nuclei changes with reaction time, resulting in the change in the concentration of type of growth units. We have these two types of growth units. Here it's shown zinc hydroxide and zinc oxide, and with the type of the growth units, and nuclei also change as the reaction proceeds, leading to the growth of different morphologies in a single sample. This is how you can see the different stages, how we can get these rods at the 5th stage. And the model 2, the other model, we have described the same formation with 3 stages, again the same growth units, and these are the different morphologies with time and concentration of gluconic acid as it changes under hydrothermal conditions. It leads to a change in the number of growth units. These are the growth units. The number changes with time that results in the growth of different sized zinc oxide nanoflowers in a single sample. So, the variation in the chemical and or physical properties of a nanomaterial or its activities occur due to its size and morphology variation. And this I am going to show from the characterization studies we have carried out. And these are the two typical samples we have selected, zinc oxide nanoflowers with two different morphologies, and sample 1 and sample 2. So we have carried out, we have calculated the band gap, the values change with the morphology between these two, and also the photoluminescence intensity change with the morphology, and this is the UV with DRS diffusive reflectance spectra, UV with spectra, and the top plot showing the band gap, and as you can see here, and this is the PL spectra of these two samples. And this is the photocatalytic activity of these two samples on in the degradation of rhodamine B under sunlight. So, and we have compared it with the third curve, that is the commercially available titania, or P25 or Degussa they call, and we have compared, and our sample show high values of photocatalytic degradation of this rhodamine B. And this is again, here we have discussed the Raman spectra and the FTIR spectra of these two samples, characteristic samples, nanoflowers of zinc oxide, exhibiting different oxygen vacancies concentration, and it varies with the change in the morphology, and this we can understand from these peaks, Raman peaks, and this is from the FTIR. You can see the splitting of the bands. And we have also carried out the XPS analysis to confirm a change in the oxygen vacancies with the change in morphology, and this has been very well accepted, in fact, and we even discussed with Professor Challapati Jagadish about this, and the change in this oxygen vacancies intensity ratio in XPS O1S spectra oxygen vacancy spectra confirms the change in the concentration of oxygen vacancies with the morphology, and this is the entire XPS spectra for the zinc oxide sample, and this corresponds to, this is of course carbon, and sample 1, sample 2, zinc and oxygen, showing the different levels of vacancies. And so we can conclude that increase in the electron concentration in the conduction band induced by the relatively high concentration of oxygen vacancies pushes the conduction band edge towards the valence band, thereby narrowing the band gap, leading to the change in the related properties, as you could see here in this wave graph. And these are the powder X-ray diffraction patterns of the zinc oxides obtained, the SEM images, and the DLS, that is dynamic light scattering patterns to show the size distribution, and the time leaf extracts and its concentration. Without any time leaves, you get such bulk, and as you increase, you get smaller particles, small size particles. And this wave graph shows the sun images of silver and palladium doped zinc oxide, and also the photocatalytic activity of the zinc oxide and the UV-Vis spectra. And we have used 3 mixed dyes and tried to degrade these dyes using the catalyst, zinc oxide catalyst, and these are some of the experiments to show how these three mixed dyes catalysts, with the variation in the dosage of the catalyst, how we could convert after treatment. Totally they are transparent and these dyes are degraded. And again these mixed dyes are degraded. And these are the different dyes. Of course it is not shown. These three different dyes, Procyon, red dye zinc and rhodamine B, and one more I forgot. Well, here I show the antimicrobial activity of the zinc oxide obtained with thyme leaf extract, and this is the control. We have selected some gram-positive bacteria listed here, starting from E. coli and typhi and P. aeruginosa and flexineri, and gram-negative bacteria we have selected here, Subtilis and S. aureus. And we have tested with these two samples of zinc oxide to see how the zone of inhibition increases with the particle size of the zinc oxide. So the zinc oxide particle size can be reduced by the appropriate concentration of the thyme leaf extract. And here it is shown here for different concentrations, 0 thyme leaf, no extract. And this is a biomolecule, and 0.5 milliliter and 1 milliliter of thyme leaf. And this shows the nanoparticle synthesized with 1 milliliter thyme leaf extract shows highest antioxidant property compared to all other in all the concentrations. So that is the result of time. And now hemolysis study has been carried out for the same thyme leaf extract used zinc oxide, and we have obtained minimum percentage hemolysis, and this is these are very good results. In all our experiments we got hemolysis less than 3% up to about the concentration of 6 mg per milliliter concentration of the zinc oxide. That's a good result. And these are the nano granules obtained in the presence of twin 80. Without twin 80, we have tested, we get bulk and highly agglomerated particles, and this is how we can control the morphology. And with twin 80, we have also tested the antioxidant activity of this zinc oxide nano granules. And as you can see here, zinc oxide synthesized with the twin 80 has higher antioxidant activity than zinc oxide synthesized without this surfactant. And also you can see here, with decrease in the size of the nano granules of the zinc oxide, the free oxygen scavenging increases as the surface area to volume ratio increases in these zinc oxide nano granules. And we have tested the photocatalytic activity of zinc oxide with twin 80, and we have achieved about 97% of rhodamine B was degraded within about 20 minutes in the presence of these photocatalysts, zinc oxide granules under UV light. And the degradation rate for zinc oxide nanogranule was almost 3 times greater than the control sample. Well, we have recycled these photocatalysts for repeated usage. We have tested about 4 times, but still the product did not change its phase. This is before and after the X-ray diffraction. I mean, after 4 cycles of the usage. So the materials did not degrade. So that's the advantage of these materials. And UV visible spectra of these different zinc oxide obtained with different surfactants like twin 80, oleic acid, gluconic acid, and the band gap energy varies accordingly depending on the surfactant. And antimicrobial activity of zinc oxide, I have compared these three samples which I have shown here in this. So you can see twin 80 showing greater than the zinc oxide obtained with oleic acid, and that is much greater than the gluconic acid. And this is because twin 80 gives very small particle size. So the smaller the size of the nanoparticles, higher would be the biological activity, which I also showed with the zone of inhibition in one of the earlier slides. And this is the comparative in vitro cytotoxicity of gallic acid reduced zinc oxide against HeLa cells using CCK8 assay. These are the standard kits available, and the biologists know pretty well about these HeLa cells and others. We have carried out this gallic acid reduced zinc oxide used. This shows very good inhibition of cellular growth of HeLa cells at all tested concentrations, and in fact the lethal dose 50% was about 200 milligram per milliliter concentration of these samples. And we have tested the cytotoxicity in vivo for this bioreduced zinc oxide using this B-Mori silkworm, and we have tested, as you can see here, this is the chemically synthesized zinc oxide treated B-Mori, and you see the mortality here, and here the bioreduced zinc oxide treated B-Mori, and this survives longer, and the bioreduced zinc oxide did not show any death even at higher concentrations. That is what we have observed in this. The cytotoxicity of honey stabilized the zinc oxide nanostructures. Again, it's evolved with 3D cells we have tested, and these are the standard assay the biologists use, and we could get at the highest tested concentration of about 10 microliters, the zinc oxide showed good growth promotion of 83% with only 17% inhibition in proliferation of cells. So some of these results are very encouraging for further biological studies, and I will touch upon the nanotubes which we have synthesized. In fact, these are some of these data are unpublished, and now they are at different stages of communication. This is the synthesis of titania nanotubes. There is a difference. There are so many papers on the synthesis of titania nanotubes, but what we have done is something different compared to what earlier people did. And in fact, we have obtained such very nice, very long tubes at temperature 130 degrees C, and we varied the experimental duration, and when we increased the experimental duration, we started getting sodium titanate instead of titania. So we could see without any what you call catalysts and others, we could get these nanotubes. The reaction time range decreases with increasing the reaction temperature. That also we have studied in detail. And this is the ideal condition, about 60 hours duration and temperature about 130 degrees C. And these are some of the 10 images of the nanotubes of titania we have synthesized. The multi-wall nanotubes with an average outer diameter of about 8 nanometers for anatase phase, and about 13 nanometers for the sodium titanate phase. We have obtained with an inner diameter of about 3.5 nanometers for anatase phase and 0.5 nearly 5 nanometers for the sodium titanium phase. We are further working on these to come out with the control to optimize the conditions. And here we have carried out the photoelectrochemical hydrogen generation using these titania nanotubes, and the photocurrent densities are shown here, and the amount of hydrogen generated is shown in this wave graph. As you could see, and it becomes very clear that titania nanotubes of anatase phase show the best photocurrent response and photoelectrochemical hydrogen generation. And also the hydrogen generation clearly obeys the first order of reaction kinetics at about 2.3 volts. Well, this is the zinc oxide nano rod work. Very recently it is accepted. Maybe in a day or two we get the DOI number for this, and it's already under production stage. And here the beauty of this work is these nano rods are in the range of 90 to 130 nanometers thickness, I mean the diameter, and they are semi-transparent in the SEM images. That is what some people have worked on these transparent and semi-transparent nano rods of this zinc oxide and the tubes in order to get special optical effects in these. And these are electronically semi-transparent nano rods. And these zinc oxide nano rods have been subjected to the XPS analysis, and this is the entire spectrum. And you have the carbon here, the absorbed carbon from the atmosphere, and the zinc peaks and the oxygen peaks. You can see here, and this indicates the presence of some considerable amount of oxygen vacancies in these zinc oxide nano rods. And there are various interpretations nowadays with respect to the oxygen deficiencies. Some people believe that the higher activity, photocatalytic activity, is because of the increased vacancies, oxygen vacancies, and some people do not believe that. They give some other reasons. Well, here we have studied the absorbance spectra, and oxygen vacancies could form donor states above the valence band, and these states would overlap with the valence band edge, resulting in narrowing of the band gap of the prepared zinc oxide nano rods that I showed in one of the earlier slides for zinc oxide prepared with some surfactant. Well, how much time I have? Okay, thank you. This is the photocatalytic activity for the phenol degradation studies. Nowadays, there is a trend. Earlier, people used to select various dyes and test the photocatalytic activity, and this has now been questioned by various researchers, and now people are slowly moving into the degradation of organics like phenol, which is highly toxic. And the phenol degradation curves are shown here, and the degradation kinetics of the zinc oxide nanorods, and also the titania, commercially available one, and the bulk zinc oxide. This is under sunlight, and the effect of the initial concentration of phenol on the degradation. And here this shows the catalyst dosage on the removal efficiency or degradation of the phenol. Well, we have been talking a lot about these metal oxides, but there are some setbacks with respect to these metal oxides. The main drawback with zinc oxide is its large band gap energy, 3.37 electron volts, facilitating the absorption of only UV light and it makes up to about 4.5% only in the solar spectrum, whereas the remaining 40% of the solar photons are in the visible range, and for the effective usage of these solar energy harvesting, the zinc oxide may not be a suitable one. And the problem with all these again is these semiconductors, metal oxide semiconductors, is the rapid recombination of the photo-generated electrons and holes. Therefore, it is necessary to extend the absorption of visible light and to enhance the charge separation for effective application. This is very important, and that is how we could conceive the idea of fabricating this compound, the cesium oxide, bismuth oxide and zinc oxide, and we have come out with some very exciting results, and this is not yet published. We are going to communicate this to American Chemical Society very soon. Well, when you subject these to the microscopic, electron microscopic images, these composites show this kind of pattern. You cannot infer any information from this from these images. But look at this. These are the XRD X-ray diffraction patterns showing the presence of all the three phases, and in as shown here, in tetragonal phase and hexagonal zinc oxide, and alpha bismuth oxide in monoclinic phase. And you can see here, you can observe very clearly the high resolution TEM image, and this is a TEM image of the same compound which you saw here in this wave graph. The same image when we subjected to the TEM analysis, well, we could understand that the size is less than 10 nanometers, maybe in the range of 5 to 6 nanometer range. And here, the high resolution image confirms the presence of all the three compounds, zinc, cesium, oxides of zinc, cesium, and bismuth, and also there the d spacings are given. This is how the product looks so fine, and we have then subjected to the XPS study of this same composite, and you can see the binding energy peaks and the peaks for cesium, oxygen, zinc, and bismuth in these composites. And the UV visible spectral image is shown, and in fact we get the best result for this 0.5 cesium, the presence of 0.5 millimolar, and this is corresponding to bismuth oxide and zinc oxide. And UV spectra of this composite with different concentrations of the cesium. We have varied the concentration of cesium from 0.25 to 1 molar milliliter. Sorry, the standard solution is about 1 molar solution we prepared for this, and we changed the concentration from 0.25 to 1 molar in the synthesis of this composite. And when you have about 5 milliliters of this 1 molar cesium oxide solution with 1 millimolar of the bismuth and the zinc oxide, nitrates there actually, the raw material, that shows the highest absorption in the visible range, indicating the enhancement of photocatalytic activity in the visible range. As you can see here, it is extending to the visible range, and this you can further understand from this photocurrent and electrochemical impedance. As you can see, in this case, this shows the highest with about this is for the 0.5 CBZ, indicating the photocurrent among all the samples tested, including the standard one, like commercially available Degussa P25. And this is attributed to the significant reduction in the recombination rate of generated charge carriers. This I explained earlier, the main drawbacks of zinc oxide or other pure metal oxides. And this helps, the presence of the cesium oxide helps significantly in what you call controlling this photo generated charge carriers. The recombination process can be controlled. And this is the Nyquist impedance plots for the different samples we have obtained. And this is the best one with this composition, 0.5 CBZ. And this shows the highest transfer efficiency of photo-generated charge carriers. And the photocatalytic activity also we have tested to understand the overall water splitting using this compound. We just tested with this sample 0.5 CBZ reaction conditions like 50 milligrams of this catalyst and 50 milliliter water and the visible light. We could get this data and the time versus the gas evolution is shown. Well, this is how we can understand these materials displayed wide visible light absorption, and this is because they form heterojunctions and they exhibit the highest efficiency in the photocatalytic overall water splitting, and particularly the study introduces a novel potential sunlight active photocatalyst for water splitting, and we are working extensively on this. And now briefly I am going to speak about the bismuth vanadate, another very attractive material, a multifunctional material showing both photocatalytic activities and also the magnetic properties. And this is these are some of the characteristic images of the bismuth vanadate with varying pH of the medium. And we have tested several dyes for their photocatalytic activity, like alizarin red S and Procyan red, and also Cibacron brilliant yellow, and we could get good results. And we have also enhanced, we have also tested this for S Aries cell wall, and this is how the activity is shown. Although excellent inhibition rate of 94% has been witnessed in case of the material synthesized with pH 8, still it needs further characterization to improve its biological activities to achieve at least about 96%. And now we have also doped this bismuth vanadate with aluminum in order to enhance the photocatalytic activity of the Procyan red MX5B, and also some textile industrial effluents collected from Reed and Taylor industries near Mysore. And similarly, this shows the decrease in the band gap energy with aluminum doping, and these are the different concentrations. Aluminum doped bismuth vanadate obtained with different experimental duration, and the band gap is varying here, and the size of these crystallites as calculated from the powder X-ray diffraction patterns, and the morphology varying from irregular shapes to flakes and monoclinic crystallites. And this is for the photocatalytic treatment of the industrial effluents and the Procyan red. when I say industrial effluents, it's the textile industrial effluent. And we have doped also with Mn for this bismuth vanadate and checked its efficiency on the band gap decreasing and also the photocatalytic treatment of the textile effluents and Prussian red. And we could enhance the efficiency of this compound, I mean the degradation efficiency. They showed a superior performance, like 94% degradation in about 3 hours time when contrasted with commercial titania, which gives about 58% in 3 hours. And bismuth and manganese, pure bismuth, vanadate and manganese doped, and the time experimental duration, and the COD, that is the oxygen deficiency, chemical oxygen deficiency, and the percent transmittance of the dyes or the effluents, and the variation in the morphologies, bowl-like flower, and layered balls and puff-like structures we have obtained. Now the last part of my talk is on the graphene, reduced graphene oxide, the synthesis of it. This is a hot topic again. Graphene with some metal sulfides and oxides as composites give very special properties, and these are some of the FISM images of graphene oxide obtained with diethyl glycol and graphene oxide in isopropanol and N-butanol. With variation in the organics, we have obtained different morphologies, and also we have synthesized the graphene oxide with microwave hydrothermal, and yesterday also this was referred, and this gives, we call it multi-energy processing of the materials, and it's very popular these days in order to enhance the reaction kinetics. And if you can control the kinetics, this can take you to the chemistry at the speed of light. I have discussed in one of my review papers on how the multi-energy processing techniques can be useful, and that forms the future of this materials technology, processing technology. And these are the Raman spectra of the zinc oxide doped graphene oxide, and the powder X-ray analysis, and the high resolution 10 image of this zinc oxide, graphene oxide composite. And we have tested this on the degradation of the dye, and using this graphene oxide, zinc oxide composite, and the data are shown here, and we could achieve about 97.72% transmittance in this with higher concentration of the zinc oxide. And we have further added aluminum into the zinc oxide and the graphene oxide composite, and these are the X-ray diffraction patterns and the Raman shift noticed, and the characteristics images, SAM images, FISM images. And also we have tested the graphene oxide against hospital infection causing pathogens, and well, we have obtained some very exciting, encouraging results. We are going further into deeper studies. Graphene oxide used in this study showed bacterial effect over S areas, and bacteriostatic effect over P. aeruginosa, and hence its use is recommended to create stable antibacterial surfaces against hospital infection causing pathogens, and we are further working on this. And this is the green reduction of graphene oxide using the plant extracts, a facile synthesis method for the biological applications. This is a very popular herb used commonly as a medicinal plant in cool area. And particularly they plant it during August, middle of August, that's what I was told. It cures several diseases. And we have taken the extract of this and used in the synthesis of this graphene oxide and tested in some biological studies, DPPS scavenging, radical scavenging activity of this reduced graphene oxide prepared with this herb has been tested here. And the cytotoxicity evaluation against Volv 3T3 cells has been understood. Also, this O sanctum reduced graphene oxide, or the popularly known as Tulsi Ras, that also we have used. And finally, to conclude, the in situ surface, in situ fabrication, especially hydrothermal method, is highly suitable for processing advanced functional material covering a wide range of simple to complex compounds with desired size and morphology, as in the case of metal oxides, vanadates and carbon-based materials. And these processes are fast becoming environmentally benign. Properties tuning like band gap, size, shape, surface chemistry, nanoporosity, optical, photocatalytic and biological characteristics could be achieved through proper selection of process parameters such as starting materials, dopants, their concentration, organics, surfactants, their concentrations, pH of the medium, biomolecules, etc. Search of novel biosurfactants and plant extracts, sorry for the spelling mistake, is an attractive area of research in the functionalization of nanomaterials. So finally, I would like to thank my group members who have contributed in this research, and thank you very much.
Excellent lucid talks on the fabrication of advanced functional nanomaterials of metal oxides.
You can hear now? Yes. So excellent talk on the fabrication of functional advanced nanomaterials, metal oxides and so on. The talk also covered the mechanism behind the morphology effect, highest antioxidant activity, antibacterial activity, hydrothermal synthesized bismuth vanadium and so on and so forth. Excellent talk. Thank you very much. Now the talk is open for discussion, comments, questions and so on.
Yes. Yeah. Yeah.
One more question, yes.
Now these are all the standard experiments in the lab, water splitting and all.
Sir, I'm just curious about different shapes of the nanoparticles which you have prepared. So have you used it for any kind of application such as biosensing or any imaging, if fluorescent materials?
I didn't use, I didn't show that work here, but we have used for bioimaging some of our compounds, the nanomaterials, particularly the titania based, and the other one is the rarer vanadate. That work I didn't show you.
Okay, one more question, last question, that you have used different surfactants such as twin 80, STS, and because these are, I think, they have toxicity in, like if you are treating in human cells or anywhere. So you have also shown that these surfactant based nanoparticle prepared, they have used as antimicrobial. So have you tried without nanoparticle, if you are treating only surfactant in the culture, so whether these will also cause toxicity?
See, here I missed one point. These surfactants are used mainly to tailor, or to give a desired functional property to the surface of these metal oxides or other nanoparticles. When once, you prepare these nanoparticles, you can remove these by sintering. That I showed, in one of the slides, how thin, the coating of these surfactants or organics, which can be easily removed without altering the size and shape of these particles. Particularly when you are using highly toxic surfactants, you have to get rid of that through sintering.
Thank you.
All right, if there are no questions, let us thank our Honorable Vice Chancellor for an excellent academic talk. Thank you very much.
So sorry, I didn't come here as Honorable Vice Chancellor.
Academic talk.
Thank you very much for your kind attention.
Thank you, Professor K. Bhairappa, for the excellent session. I now request the session chair, Professor K. A. Suresh, to present a token of gratitude to Professor K. Bhairappa.
My honor and privilege.
And now I...
Thank you.
Thank you, sir.